Hello and welcome. My name is Wolfgang Gatterbauer and this is joint work with Krishna Kumar and Paul Langton. An important problem across various branches of data science is that we often don't have enough labeled data to learn a model, yet have a lot of unlabeled data. Semi-supervised learning is the idea to combine some labeled data with large amounts of unlabeled data by leveraging some relationships amongst the data points. This may not be enough, and the idea of weak or distant supervision is to create more labeled data by using some form of heuristics, domain knowledge, or transfer from a related problem. In our approach, we do not need any outside knowledge. Instead, we attempt to leverage some algebraic properties of the inference algorithm to amplify existing signals in sparse data. For this to work, we need inference algorithms that have these nice properties. We call algebraic cheating an approach that modifies an existing algorithm in a way that preserves its overall quality, yet plants in it these properties we like. Our concrete application is node classification in undirected graphs like social networks. Here, the type or class of a node determines preferences for connecting to other classes. For example, here orange prefers blue and green prefers green. We can interpret these preferences or compatibilities as frequency distributions. So for example, 60% of edges starting at an orange node lead to a blue node, and so on. Thus we can model the compatibilities as a symmetric compatibility matrix where rows or columns represent the corresponding frequency distributions. In real life, we may have only a few labeled nodes, and we like to infer the classes of unlabeled nodes, for which we can use existing label propagation algorithms like linearized probability propagation. Now, what happens if we don't know the parameters? That's the problem we're addressing with this paper, namely, how do we learn or estimate those parameters? The state-of-the-art asks domain experts, so uses heuristics. We instead will estimate them from the few labels we have. If we know the compatibilities, then propagating them is straightforward and takes linear time in the number of edges. And the accuracy of classification is dependent on the number of labeled nodes. The fewer the labeled nodes, the worse the accuracy. If we don't know the compatibilities and try to first estimate them based on a straightforward textbook approach, based on holdout sets, we spend far more time on learning the parameters than later for propagating them. So there's a more than 2 orders of magnitude difference. Also, we observe a drop in accuracy that gets worse the fewer labels we have. Our method of learning is faster than inference. Estimation just takes 5% of the time for propagation, so we only have a negligible increase in end-to-end time needed. At the same time, our accuracy is as good as if we had used the gold standard. This means if we had estimated the compatibility matrix on the fully labeled graph. So the conclusion is there's no more need for any heuristics or domain experts. Parameter estimation has become a cheap pre-processing step before label propagation. So before we can propagate the labels, we first have to estimate the compatibilities. Now the key idea is to perform this parameter estimation in 2 steps. First, we create several small factorized graph representations, and we're going to discuss in a moment what those are. But the important thing is that their sizes are independent of the size of the graph. And we then perform the actual parameter estimation over these far smaller summaries. Now the first part is linear in the size of the graph. The second one, the actual estimation, is independent of the graph size and thus negligible for large graphs. So the 2 effects are, first, estimating a compatibility is fast, and second, these summaries capture relationships among labels over longer distances, which leads to a higher accuracy. If we had a fully labeled graph, the task would be easy. We would just need to count the number of edges of all class-to-class neighbors and then normalize. If we have fewer labeled nodes, we can still use a similar approach, yet we need to perform some optimization step. And the reason is that we can still row normalize the observed counts, but then we don't have a symmetric matrix. So we need to perform some optimization step that finds the closest symmetric doubly stochastic matrix to this row normalized matrix normalized from the counts. And the close means here L2 norm. Now what is the problem? Assume we have 10% labeled nodes. What is the percentage of edges that have labeled endpoints? It's 1%. if we have few nodes, we have even fewer edges. So the number of total observations is fraction to the power of 2 times the number of edges. The idea of distant compatibility estimation is to leverage longer paths. To see this, consider an orange node and the expected distribution of labels of its neighbors. Well, this distribution corresponds exactly to the corresponding entry in the compatibility matrix. And if we go further, we don't stop here, we look at the neighbors of neighbors. Then now, the expected distribution corresponds to the entrance in h to the power of 2. And if we go further, the neighbors of neighbors of neighbors, then the expected distribution corresponds to the corresponding column in h to the power of 3. So observe, as we go further and further away, this signal diminishes. However, we make up for it by having more and more observed data points. Let's repeat our challenge question from before. Assume we have a graph with m edges, a fraction f of labeled nodes, and an average degree d of each node. What is the expected number of labeled neighbors of distance L? Well, it's similar to before, only now we have a factor that grows exponentially with the length of the paths. Thus, the idea is that we can now use exponentially more longer paths to make up for the sparsity in data that we have. That's what we call amplification. So we gather statistics for paths of different length, and from those we then construct a distance smooth energy function. The idea being is that we have penalties for each of the path lengths and then build a weighted average over those individual penalties. We parameterize the weight with one single hyperparameter we call lambda that describes the ratio between weights of adjacent path lengths, L plus 1 and L. So for example, the weight vector is then 1 times lambda product of 2, and so on. The intuition being is that as lambda goes to 0, we just have the neighbor statistics, and as lambda gets bigger and bigger, we only have the really far distances that dominate the optimization step. And we see, indeed, it works. It works in that as we use longer and longer path lengths, the L2 norm between our gold standard compatibility and the estimated compatibility goes down. Two technical details. First, it turns out that the ideas from the previous slides gives us a biased estimator. To see why, consider again our model where we said every node has a degree 2. Well, if you look carefully, you see that this node does not have degree 2. It has 3 neighbors. The other node as well. The solution is that we need to ignore backtracking paths. The second problem arises to the fact that once we calculate powers of sparse matrices, we very quickly get dense matrix operations which do not scale. Our solution is a more careful refactorization of the calculation. This allows us to calculate statistics over 10 to the power 14 paths in just 200 milliseconds, and that's also the reason why we named our paper Factorized Graph Representations. What makes it so fast is a recursive evaluation that uses simple laws of algebra. For the intuition, consider the relational algebra expression on the right, and let's try to optimize it. We can usually speed up the evaluation by pushing the projection into the join. And similarly, we can apply the laws of associativity to matrix multiplication and keep the sizes of intermediate results from the calculation as small as possible. This idea of using a few basic algebraic properties such as associativity and distributivity for factorized computation lies at the heart of not just query optimization but many efficient reasoning algorithms in various contexts. Our paper uses the same idea of refactorizing the necessary calculations and applies it to semi-supervised learning. You find many more details in the paper and online appendix. For example, technical details on how we make learning so fast, insights on linearized belief propagation that were previously not known, insights on the properties of non-backtracking paths, and lots of experiments on real graphs. Inference over exact models like probabilistic graphical models is hard, so in practice we use approximate inference methods. like loopy belief propagation. Yet the model parameters also need to be learned, which is usually at least as hard since learning uses inference as a subroutine. In our application, we perform inference over an approximate model with nice algebraic properties. Concretely, we are using the algebraic properties of linearized belief propagation to complement label propagation with a scalable approach for parameter learning. In other words, we don't perform approximate inference over hard formalism, but exact inference over simple formalism. Thank you for your attention.